Welcome back to ECE 320A. Today we start unit number 2, which is dealing with single-phase complex power and the complex power triangle. We're still in chapter 10 in unit 2, but now you'll want to be focusing on homework number 2. And as a final announcement, don't forget exam number 1 is at the end of unit number 2. What we want to do in this video is actually define complex power, and now we're looking at something that's in a sense a complex number, and we can connect that actually with a triangle because of the horizontal part or the real part and the vertical part or the imaginary part or the apparent part, the reactive part of our power terms. Now, where do we get complex power? Well, it naturally arises because now we're in the frequency domain, we're dealing with phasors, and we now have moved our circuit elements, these resistors, inductors, and capacitors, these lumped elements, into their impedance representation, where the resistor is purely real, so it comes over Z sub R, its impedance is just R. The impedance of the inductor is J omega L, and the impedance of the capacitor is 1 over J omega C, or if we multiply by our 1, our special one, which is J over J, then we can move that J in the denominator upstairs, but it now has a negative sign associated with it. So you can see that the impedance of the inductor, if you think about this in terms of J's giving you a vertical displacement, which is orthogonal to the real component, which is the resistive component. But the inductors go up, the capacitors go opposite to that, or they actually go down in our complex plane. But now that we have these complex impedances, if we now associate those like we have with Ohm's law, or if we generalize Ohm's law, remember, was V is equal to IR. That now allowed us to connect impedances or resistances with voltage and current. We can now generalize that to have these complex impedances, and now we have complex power. Or if we look at it now as complex power consisting of a real part, which we've defined as P, and an imaginary component, which we've defined as Q, and that's our reactive power, we then end up with a complex quantity, which is our complex power. Again, the real part, we will just call the real power, or sometimes we might refer to that as the average power. And the imaginary component, we will call the reactive power. With that notation and knowing the formulas for the real power and the reactive power, we can actually now rewrite that or expand on this P plus JQ. P, written in RMS values of voltage and current, was the voltage magnitude in RMS units times the current magnitude in RMS units cosine of theta sub V minus theta sub I. That's P. And then if we add to that Q, which was V RMS, I RMS sine of theta sub V minus theta sub I. And now we have an expanded description of this complex power expression written in terms of voltage and current of a given element or set of elements. And we also have then an angle that's the difference between the voltage waveform and the current waveform's angle. We have theta sub v minus theta sub I, and that's now like that's the angle of an impedance. So you could say that this is an impedance angle for a given element, or I should say system, and that system could be an interconnected network, and so you might have theta sub v minus theta sub I being positive, negative, but some value between 0, let's say, and plus and minus 90. Another way that we can look at this, though, is by invoking Euler. We have a complex number, a real part that's P, an imaginary part that's magnitude is Q, but now if we apply Euler to this, both of these terms, the real part and the imaginary part, have the same or share the same magnitude, but now we have a cosine theta, I'll just say theta, plus j sine theta involved, but that's really just this complex exponential, e to the j theta sub v minus theta sub I. So now this connection is coming to us by applying Euler's formula. We can now convert this rectangular form of complex power to a polar form where we now have it written in terms of a complex exponential. Another nice feature now is we can, because of the way that we can manipulate complex exponentials or exponentials, we can now factor that e to the j quantity theta sub v minus theta sub I into two pieces. And let's pull the theta sub v angle term close to the voltage piece. So we now have V RMS e to the j theta sub v. And we have I RMS e to the minus j theta sub I. Or now you can actually see, I hope, that we have now written this expression for complex power. Again, this is the same complex power. It's now written in terms of a voltage phasor, a magnitude and an angle, and a current phasor, a magnitude and an angle. The only thing you need to keep clear is that that angle that we started with was this impedance angle, and so it was the difference between the voltage angle and the current angle, and now we have a minus sign associated with that current, or if we now write this complex power in terms of a voltage phasor and a current phasor, the voltage phasor now we'll just say is represented by this barred notation. That's an angle, that's a magnitude at an angle, theta sub v. And the current phasor, we have to realize that that's not the true current phasor. It's actually the negative of the angle, or we now have the complex conjugate of the current associated with the system that we're trying to find the complex power for. And the units on this is simply volt amperes. Now we have a way, anytime somebody says, what's the complex power of this system, of this circuit, of this element, if we can find the voltage of that network and its current, then the product of that voltage phasor times the complex conjugate of the current phasor produces the complex power. Another way that we can keep track of this is through a more geometric interpretation, and that's when we start looking at this complex power in the form of a triangle, meaning we have a real part. Let me see if I can do this in a colorful way. We have the real part we call P. That's our real power. And that's actually the horizontal piece of this complex quantity. We then have the reactive power, which we're labeling as Q. And in this particular illustration, or in this triangle, let me just go ahead and let Q be positive, or that would be associated with a load that was more inductive. Here is now our reactive power, which is 90 degrees different from our real power. So now we're going in the J direction. And that now, if we go from the beginning to the end, if we walked and went real part horizontal, reactive part vertical, we could have made it to the end the same way by simply going along this hypotenuse. So now anytime you see or think about complex power, you can start thinking about this complex, or this triangle, complex power triangle, that has a real part horizontal, imaginary part vertical, and a hypotenuse, which gives us the complex power. And that's now this length at a given angle. And again, the angle theta is the difference between the voltage phasors angle and the current phasors angle. And now that we have this geometric representation of complex power, now maybe it's even easier to remember the formulas associated with the real power, the reactive power, and the complex power, and a new term which we will call the apparent power, which is just the length of that hypotenuse. Let's write those down. The real power now is just the hypotenuse times the cosine of that angle, and the hypotenuse is just the length of that complex power, or the magnitude, times the cosine of theta. Again, theta is theta sub v minus theta sub I. That's our real power. We also have our complex power, which is, or consists of, in polar notation, a magnitude and an angle. Or we could think of that magnitude of the complex power actually as just, if we go back to our connection of the complex power expression, it's just the magnitude of our voltage phasor times the current, or the magnitude of our current phasor, so that here we have the voltage magnitude times the current magnitude at a given angle theta. And now we call this our complex power, as we've done before. But here, if we just want to know what's the magnitude of that power, now that's what we will term an apparent power, or the apparent power of that particular system. And the remaining quantity that we have, which we haven't yet put in play here at the end, is our reactive power Q, which is the magnitude, or the apparent power, times the sine theta. And now I hope it's a little bit more clear. When we want to talk about complex power, we have a real part, we have an imaginary part, we have the real power, we have the reactive power, and combining those in this complex way, horizontal and vertical, we end up with a complex power. But if we now had a particular circuit and we know the voltage and the current, the complex power will just be the product, keeping track of the complex algebra, of the voltage phasor times the complex conjugate of the current phasor. And that's where this complex power comes from.